Alright, well we have problem 6.14 on your homework. And this is talking about a jet. It's taking off from an aircraft carrier, and there is a catapult that's also propelling it. This jet is 17,000 kilograms. It's got an engine force. The force of the engine on the jet the whole time is about 140,000 newtons. That's 140 kilonewtons. And so this number, you're probably going to want to convert it, just so it doesn't mess you up. Just tack on 3 zeros there, and we're going to turn that into 140,000 newtons. The graph that's provided is the force of the catapult, and if you notice, this graph goes from 1,100 kilonewtons down to just 65 kilonewtons over the distance of 85 meters. So whenever you guys are reading the graph, always look at the units. The units are actually very important. Oftentimes in math, you just have numbers on these axes, and they don't really tell you much. The units really tell us something. And so what we're looking at for this problem is the work done on this catapult, or on this jet by the catapult, the work done on this jet by the engine. And so the first part, part A, says determine the work done. A says it wants to find the work done on the jet by the gases expelled by the engine during the launch of the jet. So we're looking for the work done by the engine. And you know, a lot of times you guys get confused with all this information that's being given, but this graph is the force done of the catapult by the catapult on the jet itself. So really, we don't care about this right now. All we care about is the force of the engine, and we're looking for work. And so, what is work? Work is a force applied for some displacement, some distance, and you got to make sure that you're in the same direction as that displacement. So what you're looking at is a force of the engine, which is going, these gases are being expelled one way, where the jet's being expelled the other way due to Newton's third law. Or it's not being expelled, but it's being pushed due to Newton's third law. And so really, there's no angle to be worried about here. If these gases were at an angle out of this jet for some reason, then yeah, you'd be worried about that. But really here, just FD is fine. So we're just going to take 14 or 140,000 newtons, and we're going to multiply that by a distance of 85. And if I can find my calculator, then we're going to take 14,000 times 85, and I'm going to get 119,000. Let's turn that in scientific. 1.19 times 10 to the 7th, and that's going to be the work, so that's going to be in joules. Okay, so what I might want to do is I might want to just round that to 1.2 times 10 to the 7 joules and input that. And so that's the first part of the problem. Now the second part of the problem usually trips people up a little bit more. It says determine the work done on the jet by the catapult. So we just found this is the work done by the engine on this jet. This engine gave the jet 1.2 times 10 to the 7 joules. Part B wants not the work done by the engine, but the work done by the catapult. And that's that thing that's on the aircraft carrier that the jet hooks onto, and it gets pushed along with a lot of force. It helps it really accelerate over a very short distance. And so the work of the catapult, really work is still force times distance. But we have an issue here. So we need to look at this graph, and honestly, this problem is actually very simple, but there are many advanced thoughts and concepts involved whenever you're looking at a graph, and a lot of that comes from calculus. So don't get too scared. But what we're about to do is just kind of on the basis of what calculus teaches you how to do with integrals. So the work done by the catapult is a force times a distance. Now, looking at this, what's up with the force of the catapult? Well, the force of the catapult, if you know anything about graphs, is that it's changing. So as this distance increases, the force of the catapult starts to decrease, and decreases at a linear rate, or a straight rate. Now, how the heck are we going to get a force times distance when that force is always changing? Okay, and that's where you got to think about, what if it wasn't changing? What if it was just flat? What if we just consider this bottom part here? Now, if we just consider this bottom part, if we took that force as 65 kilonewtons, that was constant for 85 meters, well, what would you be finding? You'd just be finding, well, this down here. This is the area that is underneath or in that box. Okay? And essentially what we did for part A was we took a constant force and we multiplied by its distance, and we found the area of that rectangle that it would create on a graph if we graph that. Here, what we got to do is we got to find the area of this triangle and add it to the area of this rectangle. All right, so taking a look at it, this term is called integration. And integration is basically taking very, very small pieces of a whole and just adding them all together. Now we're going to do something a lot simpler than that. That's calculus, and this is an algebra-based class. So we're going to do something much simpler by just taking these two shapes and adding the areas together. And that will give us the total force times distance. So looking at the bottom, I've got a force times distance, and that's the area, right? And the bottom says that we have a base of 85 and a height of 65, and that's 65,000. So I'm going to take 85, multiply that by 65,000, and that's going to be your force times distance on the bottom, or I guess distance times force, the way that I wrote it. And that's going to give us the area down here, but we want all of it. So how do you find the area of this triangle? It's a right triangle. Well, you find the area of the rectangle that the triangle is splitting in half, and you just split that area in half. That's 1/2 base times height, if you ever thought about it that way. So we're going to add this to the base, which is 85. And I'm going to look at the height. The height is going to be it's not actually 1,100. The height is 1,100 minus 65. So 1,100 kilonewtons. So I'm going to put 3 more zeros onto that. Minus 65. Move that over. 1,000. And that's going to give me the area of my triangle. And so once again, what we're doing, simple stuff with what we're doing with math, but pretty complex whenever you're thinking about what it really represents, is we're looking for the work. Work is force times distance, and on this graph, force times distance, the units, is basically talking about the area here. So the area of this whole shape is what we're getting. So grab my calculator again, and I'm going to find the area total. 85 times 65,000 plus 85 parentheses 11,000,000 minus 65,000, and I get a total of 9.35 times 10 to the 7th, and that is the work of the catapult. But wait a minute, we're looking for the area, so I'm going to divide that by 2. Okay, so let's go back up to my calculator here. Say, whoops, I forgot to divide that by 2 because I'm actually talking about the triangle. And my actual number is 4.95 times 10 to the 7th joules. And 4.95 times 10 to the 7 joules rounds nicely to, well, it's 5 times 10 to the 7 joules. And that would be an acceptable answer for my homework.